Welcome everyone. My name is Santiago Guanipa, and alongside my teammates Maximilian Telesco, Carlos Arvelo, and Kevin Fernandez, we're gonna be explaining flow in porous medias, what are they and its classifications. We're also gonna be explaining the Navier-Stokes equations, Darcy's law and its applications, and the Brinkman equation. So to get started, what is porous medias? Porous medias are going to be solid materials containing internal pores, which may or may not be filled with fluid. So as we can see on the image on the bottom right corner, we have kind of like the resemblance of a ant colony, where we have a solid material that contains internal pores, but is not filled with fluid. Porous medias can be described by several factors, such as the specific surface or the porosity. The specific surface is going to be equal to the total interface area divided by the total volume, and the porosity is going to be equal to the void volume divided by the total volume. We then move on into the classification of pores. As you can see on the image on the right, we're gonna have, for example, a passing pore, and a passing pore we're gonna have an inlet and an outlet where the fluid goes through. We also have a non-passing pore where we have an inlet but we don't have an outlet, and we also have isolated pores. And we can see that the total porosity can be expressed as the sum of the porosities for each pore classification. Right, we then move on to tortuosity. Tortuosity is going to be the path length between any 2 points. And then it's going to be measured by the distance between these 2 points through connected pores. The shortest path lengths can be characterized by the geometric tortuosity, where T is going to be the tortuosity, and then the L mean is the shortest path length. So as you can see in the image on the left, we have this straight path here, gonna be the one more to the left, has the minimal tortuosity of equal to 1. And on the path to the more to the right, we're gonna have the highest tortuosity here because it's the longest path. Then we can see that we have what is available volume fraction. So not all pores are penetrable or accessible to solids. The molecular properties of the particular solid, it's what is going to determine such accessibility. A simple example can be the solid being inaccessible to a pore if the solid is molecule is larger than the pore itself. The volume that is accessible to a solid is known as the available volume, and then the available volume fraction is going to be equal to the available volume divided by the total volume. That's where KAV comes from. And then the KAV is going to be molecular dependent, because different molecules have different properties and sizes, so it's going to have to vary depending on the molecule. And then we have the partition coefficient. This one's going to be the ratio of available volume to void volume. And this partition coefficient in fluid mechanics can be defined as the measure of solid partitioning at equilibrium between external solutions and the void space in porous media.
So before we delve into the later concepts pertaining to flows in porous media, we should first remind ourselves of the Navier-Stokes equation, and it is as follows on screen. It contains 5 terms: the local acceleration, or the unsteady term, the convective acceleration, or the inertia term, the pressure gradient, gravity, and the viscous term. Now, with the small Reynolds number and at steady state, the inertia term and the unsteady term in the Navier-Stokes equation disappear, meaning that the equation now predicts a fluid undergoing fully developed laminar flow. This new equation is known as the Stokes equation. It's essentially half of the Navier-Stokes equation. The entire left-hand side of the Navier-Stokes equation goes to 0, and we are left with the right-hand side, which is known as the Stokes equation. And to the right, we have an image describing the steady laminar flow profile in a circular pipe with the no-slip boundary condition, assuming that gravity is negligible. Now that we have a little bit of background on the Navier-Stokes equation, I can properly introduce Darcy's law. So In 1856, Henry Darcy conducted a study of water penetrating through a matrix of sand. Through the study, he discovered that the flow rate in a porous medium is proportional to the pressure gradient. This empirical relationship is known as Darcy's law. And now, in a homogeneous and isotropic porous medium, Darcy's law can be expressed as the following. Now, I will define each term in this equation. K is the permeability of the porous medium, mu is the dynamic viscosity, del P is the pressure gradient, rho is the density of the fluid, and G is the gravitational acceleration. And V is the average velocity of the fluid flow in the porous media. And H equals K over mu, and it is a constant known as the hydraulic conductivity. Now, the negative sign in the equation accounts for the fact that we define flow as positive in the direction of decreasing pressure. And if gravitational forces are negligible, then Darcy's law simplifies to the following, V equals negative H times the pressure gradient. Now, let's consider the experimental apparatus shown in the picture above. It is not the same as Darcy's experiment that he conducted in 1856. However, the apparatus is analogous in that the mathematical relationships discovered by Darcy's experiment are the same mathematical relationships proved through this experiment. Now, I'm going to take myself out of the screen so you can see this equation I have here. This Q equals negative K times H2 minus H1 over the change in L times the area. Now, K is still the hydraulic conductivity. It's the same H that we defined previously, big H. And the term H2 minus H1 over the change in L can be thought of as the pressure gradient. However, Q is the volumetric flow rate and A is the cross-sectional area of the porous media. Hence, the velocity, or the average velocity, can be recovered and expressed as Q over A. Now, there are some key assumptions we make in order to just apply Darcy's law to describe fluid flow. And one of those assumptions are laminar flow conditions, because it is not always valid for turbulent flow conditions. And one approach, known as the continuum approach, to apply Darcy's law to describe the fluid flow is to assume that the core scale length, which I define as big L, is much larger than the Darcy scale length, which I'm calling little l, which in turn is much larger than the pore scale length, which I'm calling little delta. Now, the volume of the region with the length scale little l is the representative elementary volume, or REV, and the pressure P is defined as the average quantity within the fluid phase in the REV. Thus, we now have a much better physical interpretation of Darcy's law, which is as follows: V equals negative H times the pressure gradient. And we're once again assuming gravity is negligible, as well as the porous medium being homogeneous and isotropic. And the last assumption that we make is that we have a very small permeability K. And this in turn implies a high fraction of solid phase in the porous medium. Now, when the opposite is true, when K becomes very large, Darcy's law will no longer accurately predict the fluid flow. If we make the same assumptions as before, small Reynolds number, which implies laminar flow and steady state conditions, then we can use the Stokes equation to accurately predict the fluid flow. This should make sense, as if the permeability is very high, then there's essentially no solid phase in the porous medium. In other words, this implies that a fluid is flowing in a channel or a pipe that contains no solid phase. Therefore, it is pure fluid flow. Essentially, we have explained how to predict the two extreme scenarios of fluid flow, a pure fluid flow through a channel or a pipe, as well as fluid flow through a less permeable porous medium. However, an equation was derived that bridges Darcy's law and the Stokes equation. This equation allows engineers to predict fluid flow in porous media when the permeability K is unknown. And this equation is known as the Brinkman equation. And I will now pass off the next slide to Kevin.
Well, as Max was saying, the Brinkman equation is the equation that links and bridges the creeping flow equation to Darcy's law. Okay, and on this slide, I'm just going to be doing an analysis of the Brinkman equation, and I'm going to be trying to show you guys how exactly the Brinkman equation links and connects these two equations together. Okay, so just to begin, the Brinkman equation I have written here on the slide is mu times the Laplacian velocity minus 1 over h times v minus the pressure gradient. Okay, where h is the effective hydraulic conductivity of the porous medium, and where this 1 over h term is equal to mu over k, where k is the permeability. Now, before we continue on with anything, it's very important to have a good understanding of what the permeability means and what it means when permeability is high and permeability is low. Okay, so I've created kind of a key here at the corner of the slide to kind of facilitate this understanding. So in the first case, we're going to look at, which is when K is high, that means that in the fiber matrix, which you can imagine it to be like blood vessels or connective tissue, there's a low fiber concentration. Okay, that means that the fluid flow is very unhindered and it more closely resembles just free-flowing laminar liquid. This means that porosity is high. Okay, on the other hand, though, when K is low, when K is small, that means that in the same fiber concentration, fiber matrix, there's now a high fiber concentration. That means that the fluid flow is very hindered. Okay, there's a lot of these interactions going on between the fluid and the solid. Okay, so in the first case we're going to look at, okay, we're gonna look at the case of what happens when K is large. Okay, when K is large, just looking at purely the mathematical side of things, we see that the Brinkman equation returns a creeping flow equation because this term obviously approaches zero, and this term, just to reiterate, is the same term as this. Okay, and when this term drops out, we see that it returns a creeping flow equation. Okay, but again, this makes sense because if we're saying that permeability is large, we're again saying that the fluid is flowing very freely and very unhindered because the permeability is high. There isn't that much stuff stopping the liquid flowing. That means that the contribution between the viscous dissipation within the fluid becomes more important than the contributions of viscous resistance at the fluid-solid interface. Okay, and we can see how this returns a creeping flow equation. Again, assuming that gravitational forces are negligible. However, now, looking at the case when permeability is very small, the Brinkman equation returns Darcy's law, because when you're making K small, okay, obviously this number now blows up because the denominator is decreasing, okay? So now this term, okay, becomes more important, and we're saying that it becomes very large and it overwhelms this term. And when we apply that, it returns Darcy's law. But again, this shouldn't make sense if we look at things from the physical side of things, because we're saying that obviously the fluid is now very hindered because the permeability is small. Okay, so there's a lot of these interactions between the fluid and the solid, and that's essentially what's accounting for. And that's what Darcy's law models. Again, as Max reiterated. Again, this is all assuming that gravitational forces are negligible. So I think this is a pretty clear explanation of how Brinkman equation models both Darcy's law and the creeping flow equation. By really accounting for the permeability of the porous medium, the Brinkman equation now returns either Darcy's law or the creeping flow equation when certain interactions overwhelm or are neglected. And now, what Carlos is going to talk to you guys about is about just some applications of Darcy's law.
Applications of Darcy's law. Darcy's law is valid for slow viscous flow. Fortunately, most groundwater flow cases fall in this category. One application of Darcy's law is water flowing through an aquifer, which is shown in the picture below. Darcy's law, along with the equation of conservation of mass, is equivalent to the groundwater flow equation, one of the basic relationships of hydrology. Hydrology is defined as the branch of science concerned with the properties of Earth's water, and especially its movement in relation to land. Thus, this law is used to describe oil, water, and gas flows through petroleum reservoirs. If we're speaking about an oil reservoir, the volumetric flux through reservoir will be smaller for more viscous or heavier oils compared to lighter oils. Once again, Darcy's law was used to obtain this information, which is ultimately allows engineers to determine the fluid flow. In conclusion, Darcy's law is a simple mathematical statement which neatly summarizes several familiar properties that groundwater flowing in aquifers exhibit. These properties include: if there's no pressure gradient over a distance, no flow occurs. These are called the hydrostatic conditions. If there's a pressure gradient, flow will occur from high pressure towards low pressure, opposite the direction of increasing gradient, hence the negative sign in Darcy's law. The greater the pressure gradient through the same formation material, the greater the discharge rate. And finally, the discharge rate. The discharge rate of fluid will often be different through different formation materials, or even through the same material in different directions, even if the same pressure gradient exists in both cases. So finally, we have the references, which are chapter 9 notes and some websites. I hope you guys were able to learn a bit about flows in porous media, and thank you guys for listening.